Okay, welcome back. Well, we just finished our discussion on spectral lines, and we referred to hydrogen and its spectral lines to help us understand the behavior of electrons as they're buzzing around the nucleus of the atom. And we talked about the fact that Bohr used the hydrogen atom to help understand these patterns. Of course, he used hydrogen atoms because hydrogen only had one electron, and like we said, if we could figure out what's happening with one electron, perhaps that could be extrapolated, and we could determine what happens with atoms that have many electrons buzzing around their nucleus. So we end up with these neat little spectral lines for hydrogen. We did a nice little lab that went along with the nature of light. This is the spectral lines for mercury vapor, and we had seen some others in class as well. Now, the atomic theory is yet going to be changed again. Let's talk about Louis de Broglie. We're just going to go through this very quickly. I want to get into the meat of this section here in just a few minutes. The frequencies predicted by Bohr for the hydrogen spectrum are essentially correct, but not exactly. Improved instrumentation has shown that the hydrogen spectral lines, these that we see here, and the lines that were predicted by Bohr, are not actually single lines. Instead, there are several lines closely spaced together, which, we can't see that in this particular image, but with very precise instrumentation, we can see that there are actually several lines very, very closely spaced together. To account for this, the atomic theory, again, had to be refined. De Broglie used Planck's idea concerning radiation and the idea of discrete amounts of energy called quanta. This theory seemed to give waves the properties of particles. De Broglie thought that if Planck were correct, then it might be possible for these particles to have wave-like properties. Now, we're not going to go through this fancy derivation. I've decided to leave this out of our notes in our curriculum for the year. But let it be said that there is a de Broglie equation that allows us to predict the wavelength of a given particle if we know that particle's mass and velocity. And sure enough, scientists found by experimentation that in some ways an electron stream acted in the same way as a stream of light. And when you think about that, electrons are so tiny, almost practically massless. They are similar once again, to photons of light. So it shouldn't surprise you that something so tiny might be able to have properties similar to that of light. Furthermore, the wavelength of electrons was exactly what de Broglie had predicted. So we are left with this question: is an electron acting as a particle, as Bohr thought, or as a wave, as de Broglie had thought? And the answer simply is yes. Now, that's sort of strange, but what I'm trying to tell you there is that we have this dual nature of an electron. Yes, it behaves like a particle. Yes, it behaves like a wave. So it has properties of both. We won't do this problem here. Like I said, we're going to skip that calculation. 1927, Werner Heisenberg pointed out that in order to find the exact position of an electron, we must be able to look at it. Well, when we look at an object large enough to see with our eyes, we're actually seeing the light waves the object has reflected. A similar thing happens when a radar sees an airplane. In other words, for us to see an object, it must be hit by a photon of radiant energy. Now, this has a negligible effect on an airplane or any other object that we can see. However, the collision between a photon and an electron results in a large change in energy for the electron. So if we can see an electron with some sort of radiant energy, we would have not known its velocity because the collision between it and the photons would have changed the velocity. Thus, we might know the position, but we don't know the velocity of the electron any longer. On the other hand, if we can measure the velocity, the electron's position changes. Heisenberg simply stated that there's always some uncertainty about the position and the momentum of an electron. This became known as the Heisenberg uncertainty principle. the same time, Erwin Schrödinger. Scientists found themselves unable now to describe the exact structure of an atom. Heisenberg stated that the exact motion of an electron was unknown. Remember, Bohr's model predicted that we could do that. Notice that Heisenberg treated the electron as a particle, but what if we treated it as a wave? Schrödinger treated the electron as a wave and developed a mathematical equation to describe its wave-like behavior. This equation is described on pages 105 and 105 of your textbook. Don't concern yourself with the equation. The point is, he was able to find an area of high probability where the electron could be found. The electron moves around the nucleus, passing through points of what we call high probability more often than through any other points. The electron is traveling at a very high speed. If the electron were visible to the eye, it would appear to look like a cloud. Now, think of this as what a fan might look like when it's turned on. The blades are moving so quickly we can't see the individual particles, but we can see a blur or a cloud appearance of what those blades are doing because they're moving so quickly. Electrons buzzing around the nucleus of an atom would have a similar electron cloud type of appearance. Thus, the orbital of an electron is often referred to as an electron cloud. Schrödinger's equation has helped us devise a set of quantum numbers to describe the position of an electron orbiting the nucleus. And that's what we want to focus our attention on for the rest of today's discussion. This is called quantum mechanics. Please put your thinking caps on and follow along. We're actually going to go through this a couple of times, and I would strongly encourage you to review this video, not just once, but several times. Now, in order to locate an electron in an atom, there are 4 quantum numbers that give us an idea as to where the electron is. For each quantum number, there's a physical representation and mathematical values that a particular number can have. We can think of these 4 quantum numbers as an address for the electron. We might have the state that you live in. We might have, in addition to the state, the city. We might even have the street name and eventually the house number to find your exact location. We can have a similar set of numbers that could represent the location of an electron as it buzzes around the nucleus. The first quantum number is relatively easy to understand and envision. We call it the n quantum number. This n quantum number represents the energy level the electron is in. Mathematically, n is an integer. An integer is a whole number quantity greater than or equal to 1. So simply put, if the electron is in the first energy level, now that's the energy level that's closest to the nucleus, its n quantum number would be 1. If it were in the fourth energy level, so not the first, the second, the third, but the fourth energy level away from the nucleus, we would say its n quantum number is equal to 4. So the n quantum number is the energy level that the electron is in. The greater this number, of course, the higher the energy level, and the more energy that that electron can have. Now, the font on this isn't the greatest. This is the L quantum number, but on the word program I'm using, whenever I type a lowercase l, it sort of looks like the number 1 and can get somewhat confusing. So I use this integral sign when I make it look more like an L right here. That's how I like to draw it in class, the L quantum number. This number represents the sublevel that the electron is in. Mathematically, L is an integer with possible values that range from 0 up to n minus 1. Now that n refers to the energy level that we talked about just a few moments ago. So for instance, if I have an electron on the fourth energy level, n is equal to 4, that means L can have the following numerical values. 0, remember L ranges from 0 to n minus 1, so it can have values of 0, 1, 2, or 3. Let's say we were on the third energy level. What can the numerical values for L be? Well, L can equal 0, 1, 2, or, well, that's it. because m minus 1 would be 2. If we were on the second energy level, n equals 2, L's numerical values could be 0 or 1. Notice, please, that if there are 2 energy levels, there are 2 values for L. If there are 3 energy levels, there are 3 values for L. And as we stated earlier, if there are 4 energy levels, there are 1, 2, 3, 4 values for L. And of course, if there were 8 energy levels, there would be, you guessed it, 8 values of L. What would they be? Well, they'd start at 0, and then we'd have 1, 2, 3, 4, 5, 6, and 7. Now, these first 4 values of L actually have special names that will have to be learned. When L is equal to 0, we call that the S sublevel. Now, S stands for sharp, but we no longer use the name, we just refer to it as S. When L is equal to 1, we call that a P sublevel, and the P stands for principal. When L is equal to 2, we call that a D sublevel, and that stands for diffuse. And when L is equal to 3, we call that an F sublevel, and that is for the fundamental. But once again, we don't use these names any longer. We simply use the letters that those names begin with, S, P, D, and F. So just as a quick recap before we move on, the first 2 quantum numbers are N and L. N represents the energy level that the electron is in. Its numerical values need to be integers greater than or equal to 1. For instance, 1, 2, 3, 4, 5, 6, and so on. Within each energy level are sublevels. Those sublevels are designated by the L quantum number. The number of sublevels relates to the energy level. For instance, the first energy level can have only 1 sublevel. If n equals 1, recall that L can be 0 up to n minus 1, and 1 minus 1 is 0. So there's only 1 sublevel on the first energy level, and its numerical value is 0. If the numerical value is 0, we call that an S sublevel. On the second energy level, there are 2 sublevels. L can be 0 or 1. So we have an S and a P sublevel on the second energy level, and only an S and P. On the third energy level, there are 3 sublevels. Their numerical values are L equals 0, 1, and 2. Their names are S, P, and D. And on the fourth energy level, and generally speaking that's where we stop in this type of discussion, there are 4 sublevels, 0, 1, 2, and 3. Their names are S, P, D, and F. Now, if we were worried about the 5th energy level, how many values of L would there be? Think about it. They would be 0, 1, 2, 3, and 4. Right? 0 to n minus 1. There would be 1, 2, 3, 4, 5 sublevels. Their names would be S, P, D, and F. And after F, we would just go alphabetically. So after F, we would run into G and H, and so on for other energy levels. All right, let's stop right there with the L quantum number. And with the next video, we'll pick up on the shapes of these sublevels. So still discussing the L quantum number. And then we'll talk about the M quantum number, sometimes called M sub L, and the S quantum number, sometimes called M sub S. So we'll do that next time. Stay with me. Thanks. Bye-bye.